I'm Syun'ichi. I'm going to talk about the development PyMFEM Python binding platform, Python binding for MFEM and scalable RF wave simulation for the nuclear fusion. And I will first start my talk about the second one, scalable RF wave simulation. And then I will move on to the Python binding development. I'm Syun'ichi from Princeton Plasma Physics Laboratory. I'm working on the RF-SciDAC, and I would like to thank everyone in this project. Just to introduce what we are interested in at SciDAC Center, the main interest is radiofrequency waves in plasmas for the magnetic fusion. And this kind of waves in the plasma, as you know, does exist everywhere. We have been using this kind of waves for the long distance communication, of course. And if you go to the sun, there's other types of wave interacting with coronal activity on the sun. And we use these waves for the fusion, especially magnetic fusion, where high temperature plasma is confined by the strong magnetic field. And we want to route the radio frequency wave to such a plasma. And this is a picture of the ITER being built in southern France. And this on the bottom is the antenna structure to launch the waves. So what we want to model is how the radio frequency wave is launched from this complicated and gigantic antenna structure and how it propagates to the plasmas. And mathematically, this kind of simulation boils down to solve the Maxwell equation in the frequency domain, but with very strongly anisotropic, spatially non-uniform dielectric materials, and sometimes spatially dispersive materials. And such a simulation presents a variety of challenges, which leads us to the development of versatile finite element analysis framework I'll talk about later. And such a simulation, for example, they need to handle the complicated variety of antennas. Over the years, people developed variety of antenna structures which they think suitable to run the waves. And we use a very different broad range of frequencies from tens of megahertz to 100 gigahertz. Due to that, antenna structure has a lot of varieties, and as you can see, it's geometrically quite complicated. And plasma is anisotropic, which means wavelength changes as it propagates and dramatically. And so even in the frequency domain, once the frequency simulation, you have a various variety of wavelengths, and the wave is launched from the right in this top one, and as it propagates, the wavelengths become shorter, and also polarization changes. And this 2D simulation is the other example. As you can see, two significantly different wavelengths exist in the same simulation. And I brought, for the illustration, the simple case where the wave is propagating in the different directions, but it's not necessarily the case. Sometimes they cross each other, then it's even more complicated. And I would like to note that this background plasma for us is not really uniform and often turbulent. And these three photos is taken from variety of various tokamaks. On the top is a photo taken from the mass tokamak. And you can interpret this different brightness as a different density of the plasmas, which means wave dielectric property it changes spatially. And also, if you launch a wave to such a plasma, you will change this nature of the turbulence. And so wave and turbulence interact each other. So before going to the high fidelity large scale simulation, I would like to note that on the RF-SciDAC Center, we adopted the MFEM library for extensively to develop the new generation of RF simulations. We rely on it from prototype development to the final production level application development. And here we brought a couple of things developed by members in the SciDAC Center. And the left bottom one is a time-dependent transport simulation, which solves the energy and momentum continuity coupled equation in the DG scheme in the finite element. The middle, this is done by Mark. And the middle one is the Socrates' work, which looked at the DD domain decomposition-based sweeping preconditional, which is an effort to come up with a good preconditional for the frequency domain Maxwell equation, which is known to be difficult to do that. On the right is the demonstration of AMR adaptive mesh refinement to resolve the lower hybrid wave simulation, lower hybrid wave with a minimum degree of freedom. We are also using this MFEM library to modernize the Fokker-Planck solvers, which we have been using, but we are hoping to get this done, so that we can take advantage of GPUs. So early on, we heard that there's 4 types of people who are interested in the high fidelity simulation. We definitely want to have the high fidelity simulations because we want to solve the wave propagation as realistic as possible. But I tend to think which one is us, and we tend to think none of them. We are somewhere in between, because we care final result very much, but we are not really engineering. We want to know the physics correctly. We are not really computational scientists. H1 curve, weak form. If we can bypass, it is ideal for me at least. So that's the reason why we came up to this Petra-M simulation environment, which stands for physics equation translator for MFEM. As it indicated, basically, we don't want to say work on weak form. We want to think about physics in Maxwell equation. That this name, the reason of this name. Over the years, however, it evolves to become integrated multiphysics finite element platform, where we can do the finite element analysis in the same place, from geometry creation to the visualization in one place. It is developed based on the variety of open source softwares. Many of them is developed by the Oscar people, but also we use the Open Cascade, the CAD library, and also meshes. And we designed this tool so that we can define the partial differential equation in an arbitrary way to figure, so that we can explore what is the best equation to model the phenomena in front of us in the experiment. Here's Petra-M is developed in a way to use a fully graphical user interface based. So here is a typical desktop of the Petra-M. And you can see that, the three-dimensional geometry is loaded from the CAD, and you can even create this kind of geometry inside the Petra-M. We have the Python interface here. You define the equation, you define the material property, you can, that's sort of thing. You can create a mesh inside, just click on the mouse click, and you can select the geometry and domains to define the material properties through the graphical user interface. And this is for the Maxwell equation. So you here epsilon and mu and sigma permittivity and permeability, typical things can be can be set by instead of weak form. We also have the weak form interface, where you can basically pick the integrator, which is implemented MFEM. And so you can try different types of equation to solve. And of course, we submit this the simulation model to the cluster from this interface and get the plot result in one place. So we have been using this in the SciDAC Center and applied it to a variety of tokamaks by now. And these are the simulation RF simulations done by a member of this SciDAC center. Some of them is actually done by the outside collaborators who contacted us to work together. And at the PPPL, we are more or less more focusing on extending this simulation capability to the large scale whole device scales wave simulation. And this is the high harmonic fast wave field simulation on the NSTX. And this kind of simulation has been difficult, mainly because I think the degree of freedom we can handle is limited due to 50 to 100 million degree of freedom due to the fact that we are constrained to use the direct solver because frequency domain Maxwell is hard to pick condition. But thanks to the fourth order and higher order capability of MFEM, we are able to resolve it for the first time. And you can see that we are about 15 wave oscillation inside the simulation domain, and which is actually close enough to what is required to resolve the ICR wave field on the ether. And we are now working on this wave simulation for the ether right now. So let me switch gear to the PyMFEM, which is this orange region in our Petra-M code structure. And so originally we developed this Python wrapper because for the electromagnetic simulation, but as you know, the Python is easier to use its interpreter. So often, so it is useful for the many things. For example, prototyping, rapid application development. It is also used for education, demonstration, and analysis using MFEM simulation output might be good way to use it. And thanks to many people, couple of people helping us, this Python, you can use this Python binding from my binder, and just use this interface so that you don't even need to install it. You can install it through the pip. Just pip install MFEM will install it on your computer. And these things are also in open source in the GitHub and are freely available. And just to emphasize, PyMFEM allows for writing the MFEM application without using C++, but it provides the convenient access to almost all, I hope, many of almost all classes of MFEM classes with Pythons. And if you look at the code, and many of the examples, except the one case, is already translated to the Python. And if you compare two of them, you can see that the code is almost identical and easily translatable. And we extended the MFEM a little bit so that we can use this wrapper from Python user-friendly. And for example, object construction, data access can be done from NumPy. We also implemented a number-based coefficient, which is important because in the PyMFEM, you can write a coefficient in Python. But what will happen is MFEM, if you call assembly in MFEM, it go back to the C++. Then from C++, it comes back to the Python to compute the coefficient. So as you can imagine, it is not so efficient. So instead, if you use number, the number is a Python compiler. So therefore, all the computation can be done in the C++ side. We also use support the MPI-based parallelism, and often, as you know, the metrics in the MPI version is distributed. So we provided access to such a hyper distributed matrix, and we provide the tool to convert it to the SciPy sparse matrix in Python. We attempted to expand to support ever-expanding list of MFEM features as much as possible. MPI use-based parallelism is there, GPU support is there, you can use device things, libc support is recently added. But I just want to emphasize that mainly this it is developed so far developed by one person at PPPL and plus some of the robots, which is basically GitHub in actions. More than welcome. It is more. I'm started to worry. Just I saw the Tani was ever increasing number of lines. I started to be worried. The day will come that it will be beyond the one person's capability, and help is really welcome. So to motivate people to join this project or look at seriously, I would like to go over a little bit to how things are done in the Python PyMFEM. PyMFEM uses SWIG wrapper to generate the most of the wrapper code. SWIG is basically the automatic wrapper generator. It takes the C++ header file and small wrapper recipe file, which we need to provide. Then it will create the C extension for Python, which is CXX file, and then a Python extension proxy module. So basically what happens is the class in C++ becomes class in Python, which is written in Python. And then from that class, C++ method is called. And of course, almost everything is automatic, but in order to make it a little bit convenient for the wrapper users, for example, C array need to be accessible as a NumPy array, or a pointer argument. In a C, it is often pointer argument is used as a return value. Instead, in the Python convention, return value need to be left-hand side of the equal. And that kind of thing need to be manually tweaked in the recipe files. So just to show the code structure, in PyMFEM, there is a serial version and parallel version, and from PyMFEM, and so the actual code is stored under MFEM _star or _par, and serial version is meant to be standalone and no external dependency. It is used for my binder use for this, and what is there in the _star is loaded to MFEM star namespace. So in other words, when you use serial version, you use import MFEM star as MFEM. And correspondingly, in the parallel version, you use MFEM par as MFEM to use MFEM. And this one is built by default. It's built with hyper and matrix, but also you can build with CUDA, for example. So generally speaking, sometimes we need to update Python MFEM wrapper code. And there's typical, these two cases is typical two cases we need to do. One is API changes in MFEM. For example, a new overloaded class method is added. Then there's a corresponding wrapper, wrapper is needed, so compile will fail. And easiest case, you can just simply regenerate the wrapper code by calling Python setup.py install with SWIG. And this option will run the SWIG wrapper and regenerate the wrapper. And sometimes, as I mentioned, a recipe file may need an update so that it can, in the resultant wrapper is user friendly in the Python. A little bit more complicated version of this is when the new header file is added. In that case, one need to add an interface file. And my suggestion, standard way to do it is to take a simplest existing recipe file like triangle I, this is all. This is just 27 lines, and modified. And of course, SWIG documentation here is a good place to look at how to do it. But it's essentially rather simple in the code structure wise. First, there's two things to change is first, the first line define the name of modules defined in the Python. So here, this triangle need to be changed to the new header file name. And then at the very end, you need to change the header file to load so that. Then somewhere in between, there's a places where to describe dependency, and then there's customization part. So I'm sorry, read. Okay, once the MFEM recipe file is made, then you need to change the setup.py so that this module, extension module, is recognized in the setup, and then that way it is compiled and built. And then last thing to do is to load that new module to the MFEM SAR and MFEM namespace. Okay.
Syun'ichi, sorry for interrupting. Do you have many more slides? We're a bit over time.
This is last slide.
Okay, excellent.
Okay, and documentation still need improvement. We just started to migration to the Python notebook, Jupyter notebook, and I hope this will help people to explain how to use it more. And waiting for contribution suggestions.